Good afternoon again. Thank you for the introduction. First of all, I would like to acknowledge all the co-authors of this presentation. This work is the result of a collaboration between an Italian team from CMCC and the Israeli team from Tel Aviv University, Israeli Meteorological Service. Okay, in this work we have evaluated the capabilities of the regional model COSMO-CLM at different resolution in reproducing the main climate features of the MENA CORDEX domain with a special focus over Israeli region located in the near coastal eastern Mediterranean areas. MENA CORDEX is one of the last official CORDEX domain. It includes North Africa, Southern Europe, and the whole Arabian Peninsula, and offers considerable challenges for regional climate modeling due to the complex topography and the great climate variability. The regional downscaling over MENA CORDEX domain is driven by several needs, for example, the assessment of the impact of climate change on water resources and the consequent socioeconomic and environmental vulnerability. Then, as I said before, we have focused our attention on a smaller domain centered over Israel for two reasons. The first one is that this region is expected to become too hot for humans by 2070. Then it's characterized by quite frequent torrential rain events and floods, so it's important to prove that the model is able to reproduce this phenomena. This is the outlook of my presentation. We start with the description of the configuration used for COSMO-CLM. Then I will present some results concerning evaluation over MENA CORDEX domain employing two different resolutions, 0.44 and 0.22 degrees. Then I will show you some results related to the very high resolution, about 8 km performance over the domain, including Israel, using detailed observational data sets, with particular emphasis on the evaluation of the capability of the model in reproducing extreme events. Most of the results that I'm going to show have been published in two papers, the first one in Meteorology and Atmospheric Physics, the second one in International Journal of Climatology. Okay, as you know, COSMO-CLM is the climate version of the COSMO model system. It's a three-dimensional non-hydrostatic regional model developed by the CLM community. In this work, we have optimized the configuration of the model, performing a sensitivity analysis. Namely, we have performed 26 small runs in order to test the effects of several parameters on the quality of the results. At the end, the optimal configuration is characterized by the parameterization of albedo derived by MODIS data, NESA-GIS AOD distribution, a third-order Runge-Kutta scheme for time integration, and the TIDC parameterization scheme for convection. This work we have used the model version COSMO 421 CLM2 and as interpolator into LM 1.19 to generate boundary and initial conditions. As I said before, we have performed simulations over the whole web MENA CORDEX domain employing two different spatial resolutions. The official CORDEX domain, physical domain, MENA CORDEX domain is one indicated by the black line. Then we have used the computational domain, which are a little bit larger. So the blue line represents the computational domain used for the 0.22 degrees resolution, and the red line represents the computational domain used for the 0.44 degrees simulation. And we have performed the simulation, INDCAS simulation over a time period of 1979-2011, skipping the first year as a spin-up. Simulation was forced by our interim reanalysis. And we have performed the evaluation against 5 different data sets, since this is an area which is characterized by lack of observational station. So it's important to quantify also the uncertainty which affect different data sets. So we have used the CRU, MERA, GPCC, GPCP, and UDEL. Then, as I said before, we have performed also a simulation over a domain centered on Israel, employing a very high resolution, about 8 kilometers. Also, in this case, we have performed a sensitivity analysis first, and then INDCAS simulation over the same time period. This simulation was forced by the output of MENA CORDEX simulation at 0.22 degrees. To evaluate this simulation, we have used 4 different data sets: the high-resolution Aphrodite dataset over Israel, CRU, KNMI data archive, including Israeli observation data, and a collection of station data provided by Israel Meteorological Service. This is a daily values dataset, so it's very useful for the evaluation of extreme events. The picture on the left shows the orography of Israel as described by COSMO at 8-kilometer resolution, while this picture shows the distribution of station related to EMS dataset. So let's start with the analysis of the results. This picture shows the maps of the seasonal bias of 2-meter temperature concerning the simulation over the whole MENA CORDEX domain, respectively for the simulation on 0.44 degrees here and for the 0.22 degrees simulation, respectively for winter and for summer, against 3 different data sets, CRU, UDEL, and MERRA. In general, we see that in winter, a strong bias is recorded over the central part, strong cold bias in the central part of the domain. Summer is characterized by dipole with a warm bias in the northern part of the domain and a cold one in the southern. If we compare the map of the bias to resolution, we can quantify the effect of the resolution on the quality of the results. For example, in winter, we see that moving from 0.44 to 0.22, a good reduction of the cold bias is registered. But in the other season, bias maps do not show remarkable changes with resolution, not only in summer, but also in spring and in autumn. These are the same maps, bias maps, but related to precipitation for the 2 resolutions, 0.44 here and 0.22 here, against 4 different data sets, the IPCC, CRU, UDEL, and MERRA. In winter, we have recorded a good representation of the precipitation pattern over North Africa. In summer, we see that precipitation over the Gulf of Guinea is underestimated, probably related to the strength of the West African monsoon, which is not properly reproduced by COSMO-CLM, while there is an overestimation over Central Africa. Concerning the effect of the increasing resolution, we have recorded a slight improvement of the precipitation pattern in some areas, in particular in the southern part of the domain. Okay, then we have evaluated the high-resolution simulation over the Israel domain, particularly in comparison with the coarser resolution simulation. This picture shows the annual cycle of precipitation over time period 1980-2007 for the 3 different simulations. The blue line is referred to the very high resolution simulation and against the 2 observational data sets, CRU and Aphrodite. If we compare the annual cycle obtained with different resolution, we see that the very high resolution simulation over Israel provides an excellent agreement with observation, exceeding, allowing a significant improvement with respect to the lower resolution simulation. This is confirmed also by the seasonal bias of precipitation expressed in millimeter month of the very high resolution simulation against Aphrodite dataset, averaged over time period 1980-2004 for the 4 seasons. We have recorded a very good agreement, especially in summer, with a small overestimation over the coastal Africa. A large bias is recorded in winter, which is, in fact, most of the precipitation occurs in this period. Then we have performed the same analysis in terms of temperature. We evaluated the annual cycle of temperature with the 3 different simulations and against 2 different data sets. In this case, we see that the high-resolution simulation is not able to improve the performances achieved at a lower resolution. And in general, the temperature is overestimated, especially in summer. This is confirmed also by this map of bias of temperature against the CRU. We have recorded general warm bias in the 4 seasons. Then, but in order to better quantify the effect of the increasing resolution on the quality of results, we have evaluated the average value of temperature and precipitation over Israel and compared with the observational value. So this table shows the average precipitation value, millimeter amount, with the three different simulations, along with the observational data set. While in this column, we have reported bias with respect to CRU. So we see that for precipitation, there is, as already described, there is a very good increase of performances with the resolution. On the other side, if we look at the value of temperature at a different resolution and the related biases, we do not see a significant improvement. A possible explanation may be the topography. In fact, precipitation is largely influenced by topography, which is better represented by the high resolution, but less so for temperature. Then, to conclude, we have evaluated also the capability of the model in reproducing extreme events. In particular, we have evaluated a set of a number of indicators, more specifically a subset of the standard TCCDI extreme events indicators. Indicators that we have considered are listed here for precipitation and for temperature. So these maps show the bias of precipitation indices based on day counts against Aphrodite dataset, averaged over time period 1980-2007. This figure shows that the number of consecutive dry days is characterized by rather large overestimation, while the number of consecutive wet days is well reproduced. The number of days characterized respectively by precipitation larger than 10 mm and 20 mm are generally well reproduced, with a slight overestimation, especially in the northwestern part of the domain. Then these are the maps of precipitation indices against Aphrodite for those indices based on precipitation daily values. We see that the 19th percentile and SDII are quite well reproduced, while 99th percentile and RX one day are overestimated, especially in the northern part of the domain. And finally, we have evaluated the bias of precipitation indicators with respect to the IMS dataset, the collection of daily value provided by Israeli Meteorological Service. Probably I do not have the time to comment on all these values. Anyway, concerning in the precipitation indicators, we see that the model reveals a good capability in reproducing these indicators. In fact, the percentage bias over the whole Israel area is always lower than 25%. For what concerns the temperature extreme event indicators, we see that the four indicators related to maximum daily temperature are well reproduced, being biased generally less than 10%. The other indicators, those based on the millimond daily temperature, are generally overestimated. So, in conclusion, the evaluation that we have performed revealed that the model is able to reproduce the main climate features of the area, especially thanks to the high resolution and to the optimized model configuration. Anyway, the results show the existence of systematic deficiencies in the Mediterranean region in the reproduction of climate features with the COSMO-CLM. We have also recorded that due to the scarcity of gauge station, there are discrepancies between different observational data sets. And finally, we have seen that the increase of resolution produces a good reduction of precipitation bias over Israel, while for temperature, the improvement are not recorded. And finally, we have seen that the model has good capability in reproducing extreme events over Israel. Okay, that's all. Thank you very much.
I guess one question I had is, when you run at 8 kilometers, you are still sort of in this gray zone.
Sorry?
You are still in this gray zone, gray resolution. I mean, it's really I wouldn't call it the convection permitting.
Yes,
so do you actually call the convection scheme at 80 kilometers?
Yes, convection scheme is active, yes.
Okay.
Yes,
so
we have planned to perform a very high resolution simulation at 4 kilometers, switching off the convection. It will be a topic of future work.
Okay, well, thanks very much. So we have a change compared to the original program. Yamina Silva is replacing Antonio Parodi with actually different talk.
Good afternoon. I will present some preliminary results from the model we are running for the Central Andes of Peru. But actually, it's not in very high resolution yet, but we are planning to run a high-resolution model. First of all, I will speak a little about the major climate features of South America. We have in Southeast Pacific anticyclone that is, we have a cold current here and very huge upwelling. That's why it's a very cold water here. And we have the low-level jet that comes from the east. It's very humid and very warm air from here. The precipitation over the Andes is related, of course, with this warm water from the Amazon, and it's cold air surface near the water surface, and the large-scale subsidence related to the anticyclone. And there's some episode for dry episode. It's related with the anomalous westerly wind here. And that's why we have the climate in Peru. We have the Amazon. It's very huge precipitation until 7,000 millimeters per year. And the very dry coast, the coast of Peru, where the most of the people, the big cities are located in the coast, it's very dry. It's 5 millimeters per year precipitation. There's a medium precipitation over the Andes until 800 millimeters per year. There's our place to study the Mantaro basin is located. It's the rainy season. Here it starts in September until April. The peak of the season, it's between January and March. Almost 50% of the precipitation comes in these months. Of course, over the Andes, because of the high altitude, the annual amplitude of temperature is also high. It's very cold in winter, and it's warm. It's more warmer during the summer. It's mostly related to the clouds and this time. The Mantaro basin is quite big for the Andes basin. Usually the basins are very small there. It's important because there is a hydropower energy comes from this basin. Also, there are important population there. Actually, there is a glacier here, but the main precipitation here is from the main water resource come from precipitation. In the valley, actually, it's small, but it's a great agricultural production here. Mostly of the agriculture in this area, it's directly depends from the precipitation. We run the WRF model for 2 domains now with 27 and 90 kilometers resolution. And there is a third domain with 3 kilometer resolution, but it runs only for some period. We ran only for 1 month to evaluate the month of the biggest precipitation from 2000 until 2012. We use the initial and boundary condition, then set final analysis with 1 degree resolution. And for evaluating the precipitation, we use the tropical rainfall measurement mission from the satellite, the product 2A25, and also the station data in this 3-box. That's what we evaluated. Because we needed to have more resolution for the topography, we changed the default resolution from the model to the Shuttle Radar Topography Mission, that's 90-meter resolution. And we used the land use actually from MODIS, but we are planning to change the land use also to more resolution. We ran the model with Thomson Microphysics, Grell-Deviney cumulus, and unified NOAA land surface model for surface processes, and Yangtze University PBL. We used the TERREM satellite data for evaluate the precipitation, but actually it's not perfect data. I show here this is the topography. This is from the Andes until to the Amazon. This is the profile of topography here. And there is some station. The bars are the station data, and the blue line is the TERREM precipitation. The TERREM tends to underestimate the precipitation over high latitude station. It's from this region from Peru. This is in the Bolivian altiplano. It's almost the same. This is for our region, for the Mantaro basin. We found this almost the same. This is the TERREM, the yellow line. The bars are the station data, and this is the WRF precipitation for this compared to this station. So one of the problems is that we have some data to evaluate the model. We have very few stations, especially difficult for the complex topography to have a good resolution that station data, has said Silvina in this morning. And we need actually to evaluate the satellite data also. This is the TERREM. To evaluate the diurnal cycle, we use it also, the TERREM. It shows the early morning precipitation and the afternoon precipitation. It shows that most precipitation comes in the afternoon. It's quite well compared to the station precipitation. This is the bars. Is the station precipitation. It comes in the afternoon between 16 and 19 at afternoon, and there is a second peak in the morning. Yes, this is just different kind of precipitation that we are evaluating. So this is the spatial distribution for every 3 hours. This is the TERREM. Here is our basin. There is no precipitation. In the morning, it starts a little precipitation, and it's the maximum at 16 hours. It seems that it's quite well compared to the average precipitation that I said from a station. This is the WRF precipitation. The WRF is overestimated precipitation, or almost a factor by 4. It's because we need to use the same scale. We divided it by 4. The WRF precipitation also presents the maximum at this time at 16 hours, but it's shifted to the east compared to the trim precipitation. In this graph, the lines show the WRF precipitation divided by 2 compared to the station data. The maximum is 1 hour before it compared to the station data. We analyze the fluxes. This is the vertically integrated moisture transport from the basin. This arrow shows the low level jet. It's quite well defined, the low level jet. It's no precipitation here. shaded here is the convergence. It shows a huge convergence here in the 16 hours. It's related to the maximum precipitation. The convergence at 16 and 19, but it's not convergence in the other hours. It seems that the precipitation in this, the peak of the precipitation is related with the huge convergence. The flows come from the east and from the west and from the east. It's related to the circulation. We analyzed also the interannual variability for this period for 13 years that we ran the model in this box. There are not actually very well results because there is the dry years. Only 2 or 3 years are well reproduced by the model. It's some years later here for this year that was a wet year, and also a wet year here. But in the other years, it's not very well defined by the model. So what we have now, it's what we are planning to do is we have here in the laboratory that was implemented recently in the Andes. We have different instruments to measure these atmospheric parameters, not only the conventional temperature and precipitation. Also, we have here the fluxus tower to calculate the fluxes, the sensitivity for the latent fluxes. Also, we have this densitometer to calculate the distribution of the precipitation, or the solid precipitation, or wet precipitation, or water precipitation, and 2 radar. It's the cloud precipitation radar and the boundary layer tropospheric radar, or wind profiler. And we will use this instrument just to understand all the processes that related to precipitation and the energy balance and the water balance in this region, in this observatory, and then understand better the model. So this is an example for these 2 hours. This is the radar data. This is the reflectivity. We have some precipitation here, and here also some convective precipitation, and we have compared it with the densitometer. We are comparing different data for precipitation, like the conventional data with the densitometer and the radar data, and also we are using the GPM satellite to evaluate the precipitation. Yes? So what we need now is to calibrate the precipitation that is produced by the satellite from the GPM using the Marshall-Palmer equation that's needed. We have the relation between the rain rate and the reflectivity, and we have this data from this is the reflectivity from the densitometer and from the radar, and that's why we use from different precipitation, the convective precipitation and the static form precipitation. This is an example. We have one day what is the wind profiler data. It's the vertical velocity, and we can see here, and then the up and down air here, and we could see in the radar data that's a convection here, there's a precipitation here, and it's we can see the clouds and we can see the precipitation in this data. So we are now interested in the microphysics of the clouds and the precipitation using this data. So in summary, we can have the world. It's very nice to have a model that we can run for this area, but now it tends to overestimate the precipitation by factor of 4 respect to the terrain, and by 2 respect to the ground precipitation. The diurnal cycle is quite well simulated by the model. The model reveals poor skill in reproducing the interannual variability of precipitation across the basin. And also the satellites tend to underestimate the precipitation over the Andes, in comparison to the observational data. What we need now is really high resolution models, almost 300 meters to the valley, to study the physics of storm and cloud and precipitation over the Andes. Thank you.
Maybe time for one question. If there is any. So I have a question. So did I see correctly that actually this convection scheme was able to catch the diurnal cycle? This GREL.
The GREL scheme. Yes, it's 9 kilometers. It's a convection parameterization.
Oh, okay. So I guess in some ways it depends where you're running these convection schemes, whether you catch the diurnal cycle or not. Okay, thanks very much, Yamina. Christoph, Thomas Schwitalla is next.
Okay, welcome to my presentation. I will talk about our convection permitting latitude belt simulation using the weather research and forecasting model. The motivation behind this is that, of course, we have feedback processes from the large to the local scale. So, for example, from low pressure systems development over the Atlantic towards the local scale over Europe. The Atlantic ocean circulation has a big impact on the weather in Europe. As we've heard in the presentations today, at current NWP domains are set up over the region of interest, which are driven by a global model, either GCM or reanalysis data. And of course, if you have boundary conditions or boundary locations, for example, over the ocean, this may lead to distortions, because usually you have different physics in the driving model and in your limited area model. The boundaries over the Atlantic can be very crucial for Europe, and also, as we've heard today, that the convection permitting resolution is very important to realistically represent meteorological processes. And of course, we had the chance to use a complete high-performance computing system to do these type of simulations. The experimental setup is the following. We used a resolution of 0.03 degrees with 12,000 by 1,500 cells and 57 vertical levels. The model top was sent to 10 hectopascals and 14 levels were up to 1,500 meters above ground. The forcing data for this experiment came from the ECMWF operational analysis every 6 hours at the north and southern part of the model domain. We use a two-moment microphysics scheme, which includes ice, snow, and graupel. We used the YSU PBL scheme, which is a non-local PBL scheme. And we also used the NOAA land surface model. This is a 4 soil layer model with a single layer snow model. It was also mentioned in one of the previous talks that SST data are very important, so we did not use the operational SST data from ECMWF, but we used the high-resolution data from the OSTIA project of the UK Met Office. The simulation period was July and August 2013, and we did not use any data assimilation or nudging for this experiment. This is the model domain. It covers the whole globe from west to east and starts at 20 degrees north, goes up to 65 degrees north. To give you an idea, the lowest point in the Dead Sea is about minus 350 meters below sea level, and the highest point in the Himalaya is around 7,900 meters. Some technical aspects, as we are talking also about high-performance computing requirements. The simulation was performed on 3,500 node of a Cray system, which is 84,000 cores in total. With MPI OpenMP hybrid mode, we used the parallel NetCDF to write out all the files. For this test, the output frequency was 30 minutes for the 3D volume data. Each output file is around 100 gigabyte in this case. And we have an output frequency of 15 minutes for 2D fields like radiation, 2-meter temperatures, and so on. We also have restart files. Each restart file is around 440 gigabytes in case the model fails or power loss at the HPC system. So the total amount of data, including pre- and post-processing, is around 450 terabytes in this case. The simulation itself takes around 1.5 days, and if you include all the output of your interesting fields, then the total required time increases to 3.5 days. So this means 2 days have to be spent in this case for just writing the output fields. To give you an idea about the meteorological situations, on top you see the sea level pressure as contour lines, and the difference between July and August 2013 compared to the period 1979 to 2012. You can see that especially over Northern Europe there's higher pressure compared to climatology, while there's a significantly lower pressure here between Greenland and Iceland. If you look at the sea surface temperatures anomaly with respect to 1979 to 2012, you can also see that the east coast of the US, the SSTs were quite warm, also in the Western Pacific, so between China and Japan. And now let's see if this animation works. This is an animation of a Category 3 typhoon, which was observed at 12th of July, south of Japan. On the top you can see the predicted track of the simulation. Actually, the observed track was around 200 kilometers shifted to the south. And this is the 30-minute resolution. This is top of the atmosphere outgoing long-wave radiation, and you can clearly see the eye of the typhoon. You can see the rain bands, the very high clouds indicated by the blue colors, and unfortunately cannot be really seen, but as soon as it reaches land, the system will be destroyed. What we also see is the stratocumulus clouds over the Atlantic. So here we have the Canary Islands, the Azores Islands, Portugal and Spain over here. And these clouds are so small that they cannot be reproduced, for example, on a 0.12 degree resolution, which I will come in a minute, because the resolution is too coarse. This is another nice result which we got. This is an animation of a low pressure system development, which starts over here and then starts to transit towards Europe. Okay, this is also 30-minute time frequency, and you can nicely see this dry intrusion here. Then later on, it's getting narrow, the gap is closed eventually, and then the embedded convection starts to develop, and then you have this classic low pressure system. To show you also some results, here you can see the average mean sea level pressure at the 12 UTC time steps averaged over July. This is the ECMWF analysis. In the lower panel, you can see the mean bias of the 0.303 degree resolution simulation. You can clearly see that there's a strong positive bias over the Atlantic Ocean, a very strong bias exceeding 5 hectopascal over the Pacific. And this bias over Asia is caused by the higher temperatures which are simulated in the WRF model, and this results in a heat low. If you look at in this particular region here, and on the next page in the bottom, you will see the same area with a 0.12 degree resolution. And over the Pacific, it looks quite similar, but over the Northern Atlantic, it looks very different. And here you have a strong low pressure systems, and at the high resolution, you have these high pressure systems over there. If you go forward to August, here we have again the ECMWF analysis. The high pressure system is moving towards the Azores Islands. Unfortunately, this pressure bias is increasing because the location of the system is not correctly simulated in this region. And if you look at the 0.12 degrees, the situation is even worse over the Pacific, and it's also worse over the Atlantic Ocean. This is what I will skip this. If you look into the boundary layer, or 850 hectopascal winds, mean wind speeds, again, this is the ECMWF analysis, this time for the 2-month period. And you can see the higher wind speeds over the Northern Atlantic, where we have the low pressure systems moving. This is the root mean square error of the wind speeds, and you can see it's quite low, except the Pacific region. And the WRF model seems to have a tendency to overestimate or to overpredict the Typhoon development in the Pacific Ocean, because if you look at the 0.12 Corso resolution, you can see that there's an even higher root mean square error. And the lower resolution really tends to produce more storms or depressions and tropical cyclones than the higher resolution. Precipitation is also very important. Here we have the Seamoth analysis, which was already mentioned. This is on a 0.25 degree grid resolution. Here we have the high-resolution WRF simulation interpolated to this grid. You can see a fairly good agreement, at least over the oceans, apart from the Pacific, where the model tends to really overestimate the precipitation. If you look at the Corso resolution, the results here in this region get even worse. Also, the precipitation over here is clearly overestimated. And this is, as already mentioned in the previous talks, the result of the convection applied cumulus parameterization. In this case, we use the Kane-Fridge scheme here. Another thing is to look into scatter plots. So on the left side, you have the lowest, the 0.12 degree resolution versus the observed precipitation, and you can clearly see the offset, and also the slope of the regression line is a little bit different. In the high resolution simulations, you can clearly see the precipitation bias, but nevertheless, the slope is quite similar compared to the observation or compared to the ideal case. To zoom into Europe, this is a picture of the precipitation PDF. On the left side, you have the Corso resolution WRF, and here you have the convection permitting simulations. The solid blue bars denote the observations, and if you compare these two images, you can clearly see that the 0.03 degree resolution comes closer to the observations compared to the 0.12 degree resolution. To come to the summary, we did the first longer-term convection permitting latitude belt simulation over almost the northern hemisphere. We have an overestimation of storms in the Pacific Ocean. This is resolution independent. The sea level pressure bias probably is caused by an interaction between the combination of the applied convection parameterization and the cloud microphysics. Another point, an important thing is that we cover a wide range on the globe, and so the cumulus scheme and the convection cumulus scheme and the microphysics scheme have to deal with different physical properties if you're going to the polar regions compared to the tropics. The precipitation is overestimated. This seems to be also a general problem of the WRF model. But two questions came into my mind. So the I/O seems to be becoming the bottleneck. So is there some room for improvement concerning data formats? Is it GRIP, HDF, NetCDF, CDF5, binary, something totally different? And of course, I mentioned the number of compute cores we used, and maybe some of you know the top 500 list, but the top 500 list unfortunately does not account for the I/O properties, so it's purely computational power. And last but not least, I want to acknowledge a few people and institutions, especially the High Performance Computing Center at the University of Stuttgart and Cray, who gave me the opportunity to perform the simulation. And that's it. Thank you.
There's one here. Okay, we can do it later. Yeah. Oh, there's one even further up.
Just a technical point with input-output with HPAC. In the IPSR, we are developing within other institutions library for input-output for edge performance. It's called XAOS, and it has been proved, and I mean, it has been used in a test simulation with 20,000 CPUs, and more or less we get rid of the bottleneck of the input-output. So, but there has to be a huge effort to implement the XAOS to the WRF, but can be a good idea to think about.
I think we'll take these two questions, and that's it. There were two questions here. No? Not anymore? Oh, here, yes. There are two questions here. Francois first, and then we'll get there.
So thanks for this very, very interesting talk. It's a relatively short simulation, but I'm wondering if simulations such as this one, and perhaps others performed over longer periods, can be used to actively try and inform the cumulus parameterizations that are used at lower resolutions. So do you have plans, for example, to study the statistics of storm dynamics in the simulation, and perhaps the microphysics towards informing the lower resolution runs that we are doing all the time? Because this type of simulation will remain unfeasible at climate change timescales for many more years.
Yeah, you mean in terms of climate simulations? So this was just a test case for the WRF model. The idea would be, if possible, we would do the experiment again for a longer time scale if you make a kind of trade-off between I/O and running time. So I'm not sure if I did get your question right, but no? It's hard to understand here, so we can talk later maybe.
Yeah, maybe you guys can talk offline. We'll take the last question here.
Thank you. That was very nice presentation. You said channel models, huh?
Yeah, latitude belt.
It's not channel, really not
I didn't
channel.
say channel model, I say latitude belt.
Yeah, okay. So you said you use Seamoth for comparison at the end. But you have two kinds of Seamoth. Which one?
For these applications, I used for the plots of the total precipitation, I used the corrected Seamoth version,
okay.
And for the scatter plots, I used the blended product, which is only available over land.
Okay. So sometimes you have to take care of your. Don't believe too much in your observation. Actually.
I know.
You may be actually right some points there.
Yeah, the problem is especially over the mountains, so especially over India, I also looked into the observations, and they are very far away from the model simulations. So I do not trust the observations in this region.
Okay, so that's it. Thank you.
Okay, thank you. We go to Christoph, Schär.
Okay. I hope I can find the right presentation. Prefer to give this one and another one. Okay, yeah. Okay. Thanks a lot. It's a pleasure to be here and to attend this interesting conference and interesting session. I should, while beginning, I will present you some simulations showing convection-resolving, not convection permitting, resolution over the European continent for a decade-long simulation. And I should mention my co-authors in particular, David Leutwiller, who has carried out many of these simulations. Well, maybe there is a... Okay. Ah, yeah. David Leutwiller and Nicolina Bahn. They both have been PhD students when this project started. Nicolina has already finished, and David is in his final run-up. Now, but while I will look at this high resolution, I actually added a slide because it's an issue which we should debate in the RCM community, which has been brought up a couple of years ago by Wilby and Desai, and also in some way, Filippo has alluded to this work earlier this morning. Wilby and Desai, they coined this term, the cascade of uncertainty, and arguing that actually the cascade or the uncertainty increases as we go from socioeconomic scenarios, greenhouse gas scenarios, GCM, RCM, and so on. So he actually said the range of uncertainty expands at each step of the process and spans such a wide range as to be practically unhelpful. And also Filippo said this morning that don't expect an RCM to improve the GCMs. Something like that. But actually the point is, what I want to make and to begin with, is that the analysis of RCM GCM shows that the opposite is the case. There is a systematic improvement of the GCM results, even on scales and with smooth variables such as temperatures. As you see here, when you plot the RCM increment versus the GCM bias. Now, I don't have time to explain this, but you have a chance to see this poster. Silje Sörlund will be happy to explain it to you. I hope you will not miss it. Now, today we will look at the next step to improve these uncertainties, and this is by switching off the convection parameterization, which is one of the most difficult parameterizations we have, and to simulate convective clouds more closely to first principles. You see here a nice example. It's only a couple of weeks old over Lake Constance, and it is become visible because we have Graupel showers in the core of this shower cell, and you can also see the expanding cold air pool that have been formed at the surface and are expanding outside. Now, the situation we have in mind more generally is the one here. You see an animation of convective clouds over a few days, actually 3 days, and every day you see roughly the same, namely the convection forms during the daytime hours and decays in the evening or nighttime hours. Forms during day and decays later. And this process is of key importance for the European summer climate because it performs an exchange, a vertical exchange of temperature and humidity, but it's also important in terms of extreme events. You see here 2 examples from last summer, flash flooding associated with convective systems. So the simulations we are looking at today are listed down here, but this work really has started in much earlier. The first simulations that can be referred to as something like climate simulations were already in the year 2000, but at that time, computer resources allowed only very tiny domain data here and short simulations. Then here is a simulation from 2010, the work from Lizzie Kendon 2012, the work from Nicolina Bahn, and now we are covering the domain shown here. I should say that actually having access to a large domain is important because our domain size matters, because the statistics of convective cells needs to develop within the computational domain. And if you take some kind of numbers from the literature, you come with some back-of-the-envelope calculation to the result, which some of the experiments have also shown, that you need a zone of 100 to 200 kilometers at the lateral boundary. So a fairly wide range around or border around your domain will be affected by the transition from parameterized to explicit convection. So very small domains, they will inevitably damage the statistics of convection. And also we need a large boundary zone. Actually in our simulations we used 50 grid points for the lateral boundary relaxations. I show you here first that these simulations really make a difference. What you see here are simulations over the Alps conducted by Nicolina Bahn. This has already been published. You see the mean diurnal cycle for a 10-year-long simulations covering this smaller domain over the Alps, but actually our Alpine domain even includes Belgium. So, and what you see in black are the observations from 64 rain gauge or 62 rain gauge stations in Switzerland, and in blue are the 12-kilometer simulation result using parameterized convection. And you see what we are aware of, namely there is a overestimation of, actually the wrong timing of convective precipitation, which takes place at lunchtime rather than evening, overestimation of wet hour frequency, this well-known drizzle problem, but even heavy events, they form at the wrong time of the day. In reality, they occur in the afternoon or evening hours, while this model makes the heavy precipitation at nighttime, probably in response to nighttime cooling. Now, if you add convection, the 2-kilometer simulation in this picture, you see that most of the differences disappear. There is a dramatic improvement of the diurnal cycle. Precipitation, mean precipitation peaks in the evening. Wet hour frequency is almost perfect, and also the heavy events show characteristics very similar to observations. We have looked into this, but I think due to time I have to skip over this. We have used this also to conduct climate change scenarios and to look at the precipitation scale with climate change. We find actually important differences between the parameterized and the explicit convection, but we also find that for all what simulations conducted, we see that the hourly scale, or that the scaling with temperature follows a Clausius-Clapeyron scaling. Now I show you some more results for the European scale simulations. So first, actually, yeah, you see a little more on what we are using. So we are using actually a version of the COSMO model that runs on GPU. And this is the large effort that has been led by Olivier Fourreau. A number of people have contributed, Betio Swiss, ETH, CSCS, C2SM. And so this new model version runs entirely on GPU. To this end, the dynamical core had to be rewritten in C++, and the parameterizations, they exploit the OpenACC compiler directives on the GPU. Should mention this also is used for operational NWP and runs on a Pitsteint, which is one of the Cray computer which has at each node actually also a GPU. Oops, that was not intended. Here you see the domain we are using, and these are the details on our simulations, 1536 squared times 60 levels, grid points, and we are able to run about 1 year in 5 days, wall clock time. So it's a fairly quick simulation, so we can do a 10-year simulation driven by ERA interim. I should mention a few aspects of this use of GPUs, because in particular for the older among us who have seen the Cray 1, which was commonly used in the 80s, it's interesting to compare now one GPU against one Cray, because the performance of a GPU, which is only half a kilo or so and costs a couple of $1,000, is 1,300 gigaflops, while the performance of Cray 1 was 160 megaflop. So it is 10,000 larger, but more than a factor 1,000 cheaper, much smaller. So this is a resource that is available, but most atmospheric models don't use it because it's too cumbersome to use it. And the main reason why it's cumbersome to use it is because our modern infrastructure is extremely heterogeneous. I show you this here. So actually the central computing elements are CUDA core and double precision units on the GPU. And now about 250 of these cores, they are combined in a streaming processor. And about 15 of these streaming processors, or not about, exactly 15 of these streaming processors are combined in a GPU. And one GPU and one CPU wake now one node. And in our case, the computer has 5,200 nodes. So it's a very heterogeneous architecture, and it means that you cannot run the code on this machine and exploit the GPU in ways as we were used on standard MPP or vector systems. Now, next I show you some of the results, and we just go quickly through the most important aspects of it. Here you see at 1 day of the storm of Kirill. It's shown here at 50 kilometers. You see the clouds in the gray visualization. Colors show you precipitation amounts, and contours show 850 hectopascal. This is 50 kilometers. You see that the center of the storm actually gets stronger at 12 kilometers, and we get even stronger at 2 kilometers. You can also see remarkable refinement of the cold frontal structures with embedded convections. I will show you some zoomed results in a moment. Actually, these simulations now have more grid points than we have pixels on the screen. So in general, to visualize the data, we have to take a look into zoomed diagrams. You may also see this wonderful cloud pattern at the southern fringe of this storm. You can see some actually trapped gravity waves to the lee of the Pyrenees, which of course will not be there in the in the lower resolution simulation. Now the first zoom is in this red domain. You see the developing cold front here at 50 kilometers, stretching from France, northern France to southern England. And so this is at 12 kilometers. You see now a much better defined cold front. And at 2 kilometers, you see how these systems actually represent well-known mesoscale structures. You see actually here the line convection taking place along this cold front, so a very strong and narrow cold frontal band. You see also there is some slanting alignment of these bands with the cold front. Is something you find described in much of the mesoscale literature. Second point shows you now the core of the serial storm, somewhat later, it's 30 hours later at the time when it has reached Germany. And here you see the 12-kilometer result, and here the 2-kilometer results, and you see also, this is the location of the main cold front. You see stretches of rain bands, and you see here also some rain bands to the rear of the cold frontal system. So if you are at an individual point, one will be able to see a series of rain bands. For the summer convection, I show you now an animation. So this is now one day or one instance in this animation at noon. And you can already see in the main effect of this high resolution in this simulation. On the left is 12 kilometers, right 2.2. And color again, precipitation. And you see that in the low resolution simulation, there is widespread weak precipitation, these bluish and greenish points, much too early, already at lunchtime, while at this time there are only some few cells active here. You see some reddish cells, convective cells. You will see more of this in the animation. I will also then show you some zoomed result later where we zoom in into this domain here to show you some aspects of this case. Okay, so we will not be able to show you the whole simulation, but I at least should have time to look at the beginning. So what you see is now the formation. Look at the right-hand side. You see the formation of convection, diurnal convection during the day. You see the reddish spot, organized convection over the continent. You see also some kind of frontal systems coming in, more interesting ones a little later in time. Now we are getting to the second day. Again, convection starts much too early in the 12-kilometer run, organized convection in the second simulation. Now I think we get some frontal system in the north. Look at the cloud structure. They look extremely realistic and fascinating. And we see some these synoptic systems moving in. I show you 2 minutes. That's about what I hoped. There was left. I think there are 2 slides. So what you see here is now a zoom in this small area. It's actually at the border of Austria, Germany, and Poland. Czechia, actually. Sorry. And so what you see here is that this system really generates cold air pools, propagating cold air pools and gravity currents in a way which is common from observations, from radar observations. You look at the upper diagram. You see the convective clouds and precipitation here. You see the cold air pools. And here you see actually the vertical wind at 850 hectopascal. And you see these bands of wind where the vertical motion is stronger than 1 meter per second. These are the leading edge of the propagating cold air pools. And where these cold air pools intersect is a common spot for the formation of new convective systems. There is actually an animation here, but I don't think I have time to show it, but you can download it from the web and look at it yourself. Just look for CRCLIM. I think it's the last slide. I think it's a good point to end, actually, to think if what would be feasible today. What I've shown you are these decade-long simulations over Europe, where we can do 1 day in about 20 minutes wall clock time. And so this is achieved by a domain decomposition, 12 times 12 domains. And that means actually we need only 144 nodes of the computer. So this is actually done on 3% of this computer. So there is another 97% of the computer one could use, and one could think of what that could help to. And so one can do the CORDEX argument. Wonder how many CORDEX simulations could we do with this system. And so here the strong scaling applies because we actually put more resources at the fixed-sized problem. So we increase the number of nodes for a given domain. And the result of this analysis is that actually we will not be much faster than a conventional CORDEX simulation, actually. So if we do actually exploit 10 nodes rather than 144, we have about the speed of a normal CORDEX simulation. But on the dedicated computer, one could in principle do a 500-member ensemble of CORDEX. One would like to see that. But the more interesting part is to look at the global simulations, because there is, in the global simulations, there's the weak scaling, meaning we can actually expand the problem size. So each processor just does its domain, and so we add processors until we have the global domain. And it has been shown that this code has an excellent weak scaling to up to several thousand nodes. And so if we have the whole resources available, we could actually do a global simulation at 2.8 kilometer simulation with 1 year in 20 minutes. So one could actually do global convection resolving atmospheric climate simulations already today. But of course, one needs to have the code that can do it, and there is no global model running on GPUs. And it also would require online analysis, because what has been discussed previously, it certainly applies to our simulation as well. Writing out the output is one of the big challenges. And it's not only the I/O itself, it's really the memory bandwidth becomes the most critical bottleneck for these simulations. So I think in a few years, we will not rerun these simulations and not store the output, but actually we will rerun the simulations instead of storing the output, because it will be cheaper. And we have if you are interested in that kind of issues, you can go at these websites. We have a project on that. Thank you.
A number of interesting points, so we'll take a few minutes for questions if there are. Maybe I can ask a question. Technical. I mean, do you see this GPU approach? I mean, I hear conflicting predictions about where the computing is going. Somebody says the future is in GPU. Somebody says no. Yeah. Can you comment on this?
Yes. So, I mean, first of all, we started this work because Thomas Schultes, who is the director of our Swiss Center for Scientific Computing, he pointed out to us many years ago that the future will be on heterogeneous hardware systems. And so maybe the GPUs come and go. That's possible, but I think what can be taken for fairly granted, at least to some of the specialists in the area, is that this heterogeneity will take over. And so if this heterogeneity takes over, it's actually the same approach. So, I mean, it will maybe have another instruction set and use something else than CUDA or so, than a GPU, but it will essentially imply the same type of algorithms.
So we'll take maybe one question so we don't get too late. There you go. We are late, so quick question, quick answer, please.
So these cloud resolving global simulations have been around for a few years. But if we look at what the CMIP6 groups are currently doing, most of them will still be running in the order of 100 kilometers in CMIP6, and here and there a group will do better than that. So despite your very optimistic and impressive vision of the future, I don't think it's realistic that very soon we will see large ensembles of cloud resolving runs. So my question is there an effort to make use of these cloud resolving runs in a systematic way, to in a way treat them as observations of cloud dynamics, so that we can make use of that knowledge to improve the parameterization schemes that we use at lower resolution?
Yeah.
That's a good question, actually.
Yeah, it's a good question. I like the question. So so first of all, I think I agree with you that it will take a long time before we will have, all of us will be working at that resolution, and there is maybe for many questions it's not needed that we work at the convection-resolving resolution. But I think there are a couple of important issues, and one is hourly precipitation peaks, which in most towns of Europe actually the sewer systems are designed for the hourly or 10-minute precipitation peak, and you will never get the right answer to the engineers if you use parameterized convection. The second point, I agree with you, so we are actually discussing, collaborating with a group and doing simulations over the Atlantic, driven by ERA interim over a longer-term period that could be used in a kind of as an artificial data source to develop convection schemes. I think that is an important point. I'm not sure whether I have understood all aspects of your question.
Well, it's a long discussion anyways. Yeah. Well, thanks very much, Christoph. I think we go to the last talk of the session, Ethan Gutmann.
Is there a pointer? Here we go. Hi, thanks for sticking around to the last talk. I'm not going to talk about the added value of 4-kilometer simulations over lower resolution. I'm just going to skip straight to the high-resolution simulations. So this is going to be work looking at continental domain simulations at 4 kilometers using the WRF model for 10-year, approximately, time slices. And this is work that's been done by really a large team of individuals at the National Center for Atmospheric Research. This is really led by Roy. I just get to stand up here and look pretty, I guess. So the main objectives of this project have been focused more on the hydrology, right? To look at the hydrometeorology and what we can learn about hydrology for future climate. In particular, looking at how snowfall and snowpack will change, but then also examining those changes under sort of a broader CMIP-5 projection of global warming. I'll talk about what that means in a minute. And also hopefully looking at extreme events, warm season precipitation, hurricanes, all sorts of things we can look at with this data set. And hopefully providing this as a community data set for others to use. So the simulation domain I thought was large until I saw the channel domain. 1,360 by 1,016 grid points covering the entire United States and then some, going well down into Mexico and well up into Canada. For those that are interested, here are the physics parameterizations we used, the time periods 2000 to 2013 using era interim forcing, and the future simulation is constructed using this PGW method, pseudo-global warming. So we're actually running the exact same weather, 2000 to 2013, again in the future, with just a changed background climate. Now that didn't come out so well. So the way this works, you compute if you can read that, a monthly mean historical climate from the CMIP-5 models. So this is averaged across 19 different models for a 30-year time period, and month by month. So we have the average January, the average February. And then you do the same thing in the future. So this is 2071 to 2100. We have this delta that is then sort of this monthly perturbation of climate that can be added back to the 6-hourly era interim data. So the weather from today, but the climate of tomorrow. So this does mean that we don't have any real changes in storm tracks, the same basic transient spectra and the boundaries. So there are things we can't look at with this, but it's a way of looking at the thermodynamic effects of climate change. And on top of simply doing these simulations, we've done a lot of work to improve the model. As we were doing the initial simulations, we found various errors in the modeling system. It's too warm in some places, too wet in some places. And so we did a lot of work to try to get the simulations to be as good as possible in current climate before doing anything else. So I'm not going to go through all of these additions. But if we just look, oh, and there's also a bug fix. So if anybody's been using WRF at high resolutions for long time periods, it's worth knowing about this bug that affects the lateral boundary conditions. Come talk to me. Newer versions of WRF have this fixed. So if you're at 3.7 or something, I think you're fine. But this is one of the biases we saw looking at wintertime cold bias in WRF. So this is the daily maximum temperature, sort of average, and this is the minimum temperature. You can see fairly large biases going down as far as -6, although in a lot of places you see there's really not much bias at all. So compared to some simulations, this might be considered really good. We wanted to try to do better. And by looking into how the land surface was interacting with the atmosphere, we discovered we could fix this by improving the vegetation-dependent snow fraction, snow melt curves. So effectively, with different vegetation covers, there should be more or less vegetation sticking out through the snow. You get a different albedo. And this actually turned out to really drastically improve that cold bias. It does slightly increase this warm bias, but I think overall it's an improvement. So. And that's just one of the types of things we did as part of this simulation. So precipitation, of course, is a lot harder. We've heard a number of people talking about how hard it is to verify some of these simulations. What I want you to do is, rather than looking at specific errors, just sort of blur your eyes and look between the monthly 2008 January from PRISM, this is an observation product, and WRF. And you can see that month to month it captures a lot of the major structures, and gets the storms in approximately the right places over through the simulation. April, May, June, July, August, September. So certainly it's not exactly the same. There are areas where WRF gets substantially less precipitation than the observations, areas where it may get more. But overall, this is a fairly good simulation for current climate. October, November, December. And then we can do a more robust analysis. This is some work Andres Prine did looking at the data set and not just looking at the biases, but computing biases and where they're sort of statistically significant by looking at a large ensemble of observational products and saying, look, if the WRF bias falls within the range of all these observational products, then it's essentially unbiased. So the areas with the hatch marks are not statistically significant in the biases, basically. So there are certainly large areas where the bias is clear, but then there are other areas you see where there's a significant bias, but it turns out that's not actually significant when you look at the errors in the observational products, basically. And you can do the same thing for temperature. Temperature is where we have some of the largest biases and this consistent warm bias in the high plains, and that's something that's been noted in a large number of other simulations. But we wanted to go further. For hydrology in the western United States, snowpack is really important. It's this critical storage component in the water cycle. And fortunately, we have hundreds of stations located at very high elevations in the mountains. Here you see one of these stations. So this is a snow gauge with a single altar windshield and a snow pillow to measure snow accumulation on the ground. So we have a lot of good measurements in the mountains that we can compare WRF to. If I now, first of all, note that I've sort of divided up the landscape into these major climate zones, in a sense, different regions. And now I'm going to show you results averaged across each of those regions. So here you see the Pacific Northwest, the Sierra Nevada, Blue Mountains. So this line is the accumulated precipitation over the time period. And then the line below it, it's actually a dotted line up here and a solid line here, but I realize you probably can't see that. This is the snow water equivalent, so the amount of snow on the ground in terms of liquid water. And what you can see is that overall, WRF does a very good job at matching the accumulated precipitation over the year, and also does a reasonably good job at matching the snow on the ground at all these sites. It does tend to underestimate the amount of snow on the ground. There's either a little bit too much sublimation or too much interception by the canopy. There are a lot of things that could be going wrong, but as a hydrologist, I look at that and say, that's a pretty good simulation. So we had a lot of confidence in how these simulations are performing in current climate. We now wanted to look at what they do in this future climate, this PGW climate. I'm just going to show you a few quick results. So temperature is, in some ways, at this scale, relatively uninteresting. It's a broad warming pattern, and this is sort of mimicking the change signal that was imposed from the CMIP5 change signal. There are some subtle features in and around the mountains, and if you zoom into specific months rather than these sort of seasonal averages, you can see some large effects due to snow albedo feedback, where you have enhanced warming in areas where the snow is melted off in the future climate. Precipitation, in some ways, is a little more interesting. So here you see the control 8-year average climatology of precipitation, the future precipitation, and then the change as both a delta and as a percentage. And so the percentage, of course, the southwest jumps out because there's not a whole lot of precipitation there to begin with. But you see large areas of changes in precipitation, and you see areas where there's a large change, but it turns out that's actually a very small percentage. But overall, what we're seeing is a net increase in precipitation due to the thermodynamic effects of climate change. So essentially, you have warmer air, more moisture, you get more precipitation. But it's also useful to look at the difference between snowfall and rainfall. So while total precipitation has increased substantially, snowfall has actually decreased quite substantially, particularly in the Mountain West, where it's this critical water resource that's relied on by hundreds of millions, well, tens of millions of people in the US. Even though total rainfall has increased. So this is the potential to impose severe issues for our water resource management, where we rely on that snowpack holding water until late into the summer and not melting until then. So to store this water in man-made reservoirs would require a huge increase in the reservoir capacity in the western US. So if I can get this to play, this is just a nice animation showing you the quality of the model. Everybody loves animations. And you can see water vapor across the landscape, but then you also see hurricanes just forming naturally in this system. And it turns out that this isn't just random, of course. This is forced with your interim boundary conditions. That was Hurricane Ivan. And so here you see the tracks from Hurricane Ivan in the observation, so HERDAT, that's this light gray line, dashed line, in the control period and in the future PGW period. So there may be a slight change in location, but that's probably not significant. There is a change in the intensity, so these colored dots are the wind speeds, basically, along this track. And not only did we simulate Hurricane Ivan, but of course we have all of the other major hurricanes in this period, some of which are not quite as well simulated as others, but a large number of them fall just right on top of the observed tracks. And so now we can start to dive into this a little bit more and look at what this means in how we might expect hurricanes to change. So this is looking at the histogram of wind speed intensities sort of averaged along all of the tracks from all of the hurricanes that were simulated during this period. And the blue histogram is the current climate, and then the green histogram is the future climate. So you see a substantial increase in the strongest wind speeds. But of course, the speed of the winds isn't the only thing that affects how much damage they impart. It also matters how large these are, and it turns out that in this simulation, the hurricanes are also getting smaller. So here you're seeing a shift to smaller radius of 30 meter per second winds. And so you might say, well, we have faster winds, but they're smaller areas. What's the net effect in actual damage terms? Well, it turns out you have to count for one more thing in that. That's the translation speed. So how fast is the hurricane actually moving? And typically what we find in these simulations is a decrease in the translation speed, which means it spends more time at any given location and has the potential to do more damage. So there's a group in the mesoscale division at NCAR that's done a lot of work on this sort of topic and developed a cyclone damage potential that wraps all of those together into one metric. And using that, we can apply that to our simulation and see that in general there's a net increase in the cyclone damage potential due purely to the thermodynamic feedbacks. So with that, I'm going to wrap up, and we can actually get out of here, well, maybe not on time, but on time. Yeah, we started late. So we've done a series of simulations. I didn't talk about the second two. We've run era interim forced simulations for 10-year periods in current and future. Actually, I think it's 13 years all told. And we're working on 2 CMIP-5 force simulations, so these will use the weather from a CMIP-5 model instead of using era interim weather. I think this is some of the first 10-plus year continental scale convective permitting integrations. Obviously, you just saw Christoph Schär's work doing similar work. And another interesting component here is the use of the CMIP-5 multi-model ensemble mean to generate the future climate. So we're not just taking one or a few climate models, we're averaging across 19 different climate models to compute sort of the mean change expected. I've also done a lot of work to improve the skill of the model simulations in current climate, and have done a lot of work to analyze how well they're doing and shown really fairly good performance in current climate, with the exception of this dry and warm bias in the central United States. And the PGW simulations show a net increase in rainfall, but a substantial decrease in snowfall, which may even pose severe problems for the water resources in the western United States. And finally, well, I didn't talk about the suppression of summer convection in the central US, but also this substantial increase in the potential for damage from hurricanes. Thank you.
So I think if there are a couple of questions, be willing to take them. Actually, I had 2, just for clarification. This CMIP-5, what scenario was it? Was it
RCP 8.5.
So it was a high end.
Yeah.
And the other question is, you mentioned that you're using nudging. Is that correct? So in some ways, your storms are constrained.
Yeah.
By the forcing.
So it's a very weak spectral nudging over only to, well, it's above the boundary layer, but it's strongest at higher levels, and it's only to the largest wavelengths. So it's not too strongly, but it definitely is nudging things a little bit. We wanted the hydrology to be as accurate as possible, so we wanted the storms to be in the right place. What that means for climate change signals derived from this, I have to admit, is potentially an issue.
All right. So if there are, okay, there's last question there for Burkhard. Yeah, just shout.
I'm not quite sure what you mean by CMIP-5 model ensemble. Do you mean you take a few CMIP-5 global models and then you build the mean and then you take the output of that and drive your model?
So the question is, he doesn't understand what I mean by CMIP-5 model ensemble and how did we create this. So keep in mind that we're not using this to generate the forcings directly. We're using the average across all 19 models to compute the mean change. So the change in temperature, humidity, wind speed, et cetera, on approximately a 30-day window. And then we apply that change to the era interim weather. So we're driving it with the exact same weather in the future, but the change is averaged across a large number of models. And there are certainly issues with that construction as well. There's sort of any way you shape it, there are going to be issues. But
well,
sorry.
This the Schär surrogate climate change. Anyways, I think we can close here. Thanks very much.